Okay, welcome back to the afternoon session. The first speaker of this afternoon session is Vladimir Gorchakov from Western University. His title is Three-Dimensional Small Covers and Links.
Yeah.
Please.
Thanks. Thank the organizer for giving me an opportunity to give a talk here. So let's start with definition of the small cover and let's fix some notation. So let Pn be a simple polytope. So simple means that any vertex is intersection of n facets, and facets, by facet I mean a codimension one. So we also need a map from the, so by this phi it means the set of all facets, so codimension one face. So we have this map to Z mod 2 group such that for any face in P that is intersection of some facets, because again it's a simple polytope, so any face it's an intersection of facets, and then the corresponding vectors for these facets, so they called the, so this map is called the characteristic map lambda, and the corresponding characteristic vectors lambda I1 and ik are linear independent. So if we have a face, then the corresponding characteristic vectors are linear independent. All right. So I also will use the following notation. So if I have face, then I have these vectors, and by GF will denote the group generated by these vectors. So GF denotes the group is generated by these vectors. All right, and now we can define a smooth manifold with two torus section, so which we will call it a small cover. So we already seen this construction today several times in different talks. So yeah, and in fact, this is more a theorem of Davis-Januszkiewicz that all the small covers can be represented as such topological model, and the definition, like another definition of small cover, and in fact, it's a smooth manifold with two torus action, such that for any point you have an open neighborhood, and the action in this open neighborhood is locally standard. So your orbit space is a manifold with corners, and we are saying that X is a small cover if this manifold with corners is a simple polytope, or more precisely diffeomorphic to a simple polytope as manifold with corners. However, we will use this definition. So the quotient here is following. So PG is equivalent to QH if and only if P equals Q and G minus H belongs to this group GF, FP. So FP is the small face which contains our P in its relative interior. So it's unique phase, therefore this is well defined. So here I should say that in this talk, this group is always will be in additive notation. So yeah, let's say it here. So remark that in this talk, I use only an additive notation, and theorem of Davis-Januszkiewicz that this space is a smooth manifold with the group action, not like two torus action, which is defined by the following formula. So if you have a G, then G act on this element just by sum of H and G. So this gives us an action on this manifold, and in particular, the orbit space by this action is Pn. So, and we say that X is a small cover over P, right? So now let me state some examples. So I will start with the toy example. So the first example is we can take a circle, and we take this circle with reflection. So there is a two fixed points, and the orbit space is an interval, one-dimensional cube. So related to this construction, so how do you get actually a circle? So you have two copies of the interval, and you glue them along the boundary. So along these 2 points, you glue them, and this is like this construction in simple case. And we can see that this action is just swaps the corresponding polytopes, and that's how you may think about these small covers. They are in fact a generalization in smooth category of real projective toric varieties. So another example, the most basic example, is RPN over n-dimensional simplex. So it's like more toric example. And now also we can take a products of the polytopes, and we can take the products of small cover, and it will be again a small cover of the product over the product of the corresponding polytopes. So in particular, if we take this n-fold product, on the first example, we see that n-dimensional torus is a small cover over a cube. So that's like some basic examples which you can keep in the mind. So now let's restrict ourselves to the case when n equal to 3, because I will speak about three-dimensional small covers, and I will speak about orientable small covers. So we have a following theorem by Nakayama Nishimura, which saying to us when the small cover is orientable. So small cover X is orientable if and only if there exists a linear map C from this group to Z2 such that for all characteristic vectors, so for all images of lambda, C on these vectors are equals to 1 for all. So in particular, in the case when n equals to 3, which is in the name of the topic, so we have that the image, so yeah, it follows from this theorem that in the three-dimensional case, the image of lambda can be either lambda 1, lambda 2, lambda 3, or we can add another vector, which is the sum of these two vectors, the three vectors. So we have two cases basically for characteristic map. And also, let's introduce more notation. So let G big be the orientation preserving subgroup of the acting tutors So we consider all elements which preserve the orientation. So yeah, now I always speak about the two-dimensional case. So in two-dimensional case, this group actually looks like the following. So we have 0 and we have the following sums. It's our orientation preserving subgroup. So now I can state the first theorem, which we will talk about today. So theorem. So consider any orientation preserving involution on small cover X, and X is always a three-dimensional orientable small cover in this talk. So consider G from G big, which is non-zero. So consider non-zero involution. Then the orbit space by this involution is homeomorphic to connected sum of k minus 1. So the number k will be defined later. of S2 times S1. So it's the first result. And now let's say a few words about how we can prove something like that. So the idea is to consider the following sequence of maps, taking partial quotients basically. So we can consider the following sequence of maps. So it's not hard to show that, so yeah, by definition of the small cover, this space is our simple polytope, right? So, and it's not hard to show that this space is actually a three-sphere, and we get this three-sphere as two copies of this simple polytope glued along the boundary. So you have two polytopes, two-dimensional polytopes, and you glue them along the boundary, and you get a three-dimensional sphere. Therefore, so let me write it. So xg is homeomorphic to two copies of P3 glued along the boundary. So therefore, we can rewrite the sequence as following: x, xg, S3, and our polytope P3. So now, what we want to show is actually that all these maps, so yeah, not that all these maps, they are all two-fold branched coverings, because they're all just taken quotient by some map. So here is taken by G, here is taken by G quotient, and here is taken by big group quotient. This one. So all these maps are taken like quotient maps. And since we work in two-dimensional case, we have two-fold branched coverings. And in this case, this map is two-fold branched covering over some link, because it's all orientation preserving. So it should be codimension 2, which is 1 in this case. And we have some k component link here. And this k is precisely this number of in the connected sum. So it's just a number of components, connected components of my link. And how do we get that this space is of such form? So basically the idea is this link is actually a trivial link. And the two-fold branched covering is determined by link. And why this link is trivial? So simply because if you look at the branching set of every map here, it's like one-dimensional graph, like GKM graph basically. If you look, it's here, GKM graph is like edges as circles. So yeah, so the branching set, when you take in this map, the branching set here will live in the boundary of your three-dimensional polytope. And the boundary of three-dimensional polytope is a two-dimensional sphere. So all these connected components belongs to a two-dimensional sphere, and therefore they're all trivial nodes. And from this we get that xj is homeomorphic to the connected sum of k minus 1 copies of S2, S1. All right. So how we can do it in examples? So suppose we have a polytope, suppose we have a characteristic map lambda. So how do we calculate this k in examples? So let me introduce some construction. Let me introduce it here. Yeah, so let me just, introduce the construction here. So the construction, how do we describe the branching set of this map in some particular examples? Right. So yeah, let me maybe show the examples because it will be easier to speak about all this on examples. So, for example, consider the two-dimensional simplex. So it's projected on the two-dimensional plane, and these lambdas are characteristic faces, characteristic vectors corresponding to the faces. So in this case, this corresponding small cover is RP3, And in this case, if it's an over cube, the corresponding cover is two-dimensional torus. So now let me introduce construction. So for every edge in the polytope, we can associate the unique element of the form lambda I plus lambda j. So for example, for this edge, we can associate the element lambda 1 plus lambda 2. For this edge, lambda 2 plus lambda 3. And so the branching set of this map, since it's just taking the quotient by this action, it's precisely the elements which are not labeled by G. So let me write it. Yeah, okay, I will try to write it here. Can I? Oh. So the branching set of this map, so the union of S1 is precisely the correspond to the. So yeah, we can say that it's precisely because recall that this space is actually two copies of P3 glued along the boundary. So it makes sense to speak about edges of this space because they just lives in the boundary of P3. So sometimes I will say that they're here, but sometimes that they correspond. So edges which like the original space, yeah, we glue like, so original space, we glue just somehow according to the characteristic map, but like here, we just glue it like along the boundary by identity map. Yeah, so in particular, this map is just reflection of two copies. So and the fixed point is just precisely the boundary of the simple polytope. So in the two-dimensional case, it's the simple case when you have like just two disks glued along the boundary. It's a two-dimensional sphere. So yeah, so we want to describe the branching set. So it corresponds to the edges which are not labeled by G. And by labeling, I mean that any edge is intersection of two facets. So I can label it by lambda I plus lambda j. So in fact, if you have such picture, then in your original space, this picture looks as for any edge, you consider a circle over this edge, as in the first example of the small cover, because over edge, so if you consider any face in the small cover, if you take the P minus 1 by this map, by the quotient map, you get a small cover over the corresponding face. So in particular, for edges, we have that for any edge, there is a small cover S1 over this edge. And so we just taking partial quotients, and some of them becoming the intervals, some of them staying the circles. So that's basically the idea, right? So yeah, and this element, when we describe the branching set of these elements, it's so yeah, this corresponding circle will be fixed by this element lambda I lambda j. So that's right. So let's try to do it in examples. So if I consider any involution here, for example, so yeah, I need to take any orientation preserving involution. So like take this one. Now, so to describe the branching set, I'm doing the following. So I'm looking on the edges which are not labeled by this lambda 1 plus lambda 2. So this edge, then this edge I do not take because some of these two vectors is lambda 1 plus lambda 2. So doing this one. Then I'm going this one and this one. So, and we get a Hamilton cycle on the simple polytope. And it's actually always the case that these circles, they will be a union of disjoint cycles such that the union covers the whole vertex. So for example, when we have only one cycle, so k equals to 1, we have a Hamilton cycle. So another example, consider a three-dimensional curve, and consider, let's take another involution. Let's take this involution. And so we want to describe the branching set of this map, which always a trivial link. So we're basically interested in the connected components of this trivial link. So again, so what I'm doing here, I'm looking at the edges which are not labeled by this element. So this will be like this one. So lambda2 plus lambda3 I do not take, so but instead I'm taking lambda1 plus lambda3. So I get the inner square and outer square as well. And this gives me that the orbit space by this involution will be S2 times S1. So in this case, K equals to 2. So therefore, and here as well, that X quotient by G is homeomorphic to S3. And in this case, X quotient by G is homeomorphic by to S2 times S1. All right. So the next result, if the quotient is a sphere, then actually in this map, like in the first map, when we have a small cover and if K equals to 1, this quotient is a sphere as well. And then we have this map has a, the branching set of this map is also some link in this two-dimensional sphere. So the next result is description of this link in terms of P and lambda. So before I will state the theorem, let me just show it in some toy example. So if you get a sphere here, then it corresponds to only one connected component here. And this connected component is actually a Hamilton cycle in our polytope. And we can introduce an order on vertices of this simple polytope just by following the Hamilton cycle. So I can start everywhere. It doesn't important, so something like that. So if I have a Hamilton cycle, then I have an order on vertex. So from this picture, what I need to consider, I actually need to consider a linear chord diagram. So you can see that I have two edges which are not in my Hamilton cycle. So I have the following linear chord diagram, just a partition, partition of this set of vertices into two element sets. So for example, this corresponds to this set and this set. And to describe the link, we basically just need to double every chord here. So in this example, it will be a hop link, something like that. And that's how you describe the link in more general situation. You always can consider this Hamilton cycle. From this Hamilton cycle, you can construct a linear chord diagram. And using this linear chord diagram, you can construct a link. So let's write a theorem. This is the second main theorem. So, and let me not just introduce some notation. So I will denote this Hamilton cycle by C. So the Hamilton cycle and the corresponding linear diagram by DC. Yeah, I can, but there's like examples. So, okay, there's no example. That's fine. Yeah, wait. Yeah, thank you. Yeah. Right. So, theorem. So, for the link, so if we have a involution such that the space is homeomorphic to three-dimensional sphere, then we get some link, which is the branching set of this map, and description of this link in following. So first of all, not components of this link is trivial. And they correspond by one by one. So it's a link. And here I have the linear chord diagram. They correspond to the chords in my diagram. And two links are linked. Two nodes components are linked. So link. if and only if the corresponding chords intersect. So, and moreover, in this case, the linking number actually will be always plus minus 1. So we cannot have something like that. So no such picture, and just basically because all of our space here, they are glued from polytopes, and when we glue these circles, like we always glue them by simple construction, just gluing along the boundary. So that's why we cannot have something strange here. It's like the motivation. So the linking number is always plus minus 1. And that's the next theorem. And I have 4 more minutes. So now let's see the other examples. So, for example, consider again a cube, but now we're taking the different characteristic function on it. So here is lambda1 plus lambda2 plus lambda3 instead of lambda3. So it's a different example corresponding to this one. And for involution, let's take this one. So the branching set will be 2 circles again, and the orbit space is homeomorphic to S2 times S1. So let's say K equals to 2. On the other hand, if we take the same characteristic map and we take the cube again, and if we take this involution, then this will be our branching set. So in red, it's a Hamilton cycle. And again, then we're in the situation when the orbit space by this involution is homeomorphic to 3-dimensional sphere, and we have some link here, which is a branching set. And the description is following. So this is the corresponding linear diagram we see. And the more convenient and more useful way to actually draw this diagram is to consider them as a graphs. So I mean links, yeah. So it's actually a description of the link, but how do we get this? How do we obtain this description? So we consider chords as a vertices, and we say that there is an edge between vertices if and only if the corresponding chords have an intersection. So, and let's give us precisely this description. So you can imagine this link as following. So you should replace every vertex here by circle, like by trivial not component, and then you just connect them. So I will not try to draw that, but you can imagine it. So there is like 4 not component, and they are linked each by n, but first two not linked. So yeah, and it always will be alternating link, yeah, in particular. And I guess it's a nice place to stop. So if you have any questions, please.
Thank you very much.